Welcome to the second chapter of the making of OutRun. We'll be going behind the scenes and discovering how the original arcade game was created and how I went about bringing it to the Amiga family of computers. Last time round we focused specifically on the road generation, but creating a successful games engine involves massaging multiple components to sing in harmony together. As a developer, your decisions can have a big impact on the quality of the final product. Where will you choose to burn CPU cycles? Where can you afford to sacrifice memory? And how might clever tricks and illusions create effects that feel far more advanced than the target hardware might allow? Without thoughtful planning, it's all too easy to code yourself into a corner, making later development increasingly difficult, if not impossible. One of the ongoing challenges of porting OutRun to a home computer was the difference in the colour palette. The OutRun hardware can display thousands of simultaneous colours without any special tricks, whereas the original Amiga chipset that was found in models such as the A500 supported up to 32 simultaneous colours on screen, although more could be achieved either by using copper-driven changes or the hold and modify mode, HAM. The demo scene made great use of hardware techniques to push the simultaneous number of colours further, but many of these techniques aren't always a realistic approach when it comes to developing a games engine. Sometimes demos do one or two things incredibly well, which can lead a casual observer to think that they can be replicated under all circumstances. But it may be that those techniques use significant CPU time or simply render other elements of the hardware unusable. A game engine has to be flexible enough to simultaneously deliver everything needed all at once. With the A1200 era, Commodore introduced the AGA graphics standard, which increased the overall number of simultaneous on-screen colours from 32 to 256. This sounds like a lot of colours, and you're probably thinking that this ought to be more than enough for OutRun. In fact, if you screenshot a typical frame from OutRun, you'll often find that fewer than 256 colours are being used at any one time. Furthermore, you can probably even colour reduce a static screenshot of the game to around 64 colours, and it will still look decent. So what's the problem? Surely this shouldn't be difficult, and why am I making a video about this? Well, the challenge is that whilst OutRun rarely exceeds 256 colours for a single frame, it uses thousands over the course of a single level. The game engine expects all of those colours to be available at any time. This is because those thousands of colours are allocated to the freely placeable sprites that can be used in almost any combination. This includes the roadside scenery, the traffic, plus the player's car and passengers. Furthermore, when you think about it, theoretically any piece of scenery could pop up next in the level, and we need to ensure that we have suitable colours readily available for it. OutRun sprite hardware can render up to 128 sprites simultaneously, although the game engine only uses 80 for the roadside scenery. Each sprite has a unique palette of 16 colours. Theoretically then, the scenery alone could require over 1,200 colours within a single frame. This doesn't factor in the other parts of the game, like the Ferrari, the traffic, the various visual effects, plus background tile maps and fonts. Now, we could aggressively reduce the overall colour palette at the expense of visual quality, but I believe that the vibrancy of OutRun's colours is part of its appeal, and this is exactly where a lot of the home conversions suffered in my view. Plus, that would be a time-consuming approach, besides which there are actually very few Amiga games that use a full 256 colour palette, so why not max the hardware out? To do this, I started by dividing the 256 available colours up into distinct chunks, or slots, that could be addressed by the game engine. For the sprites, multiple chunks of 16 colours were allocated. Instead of loading all the scenery palettes in at once, I wrote a palette caching engine for those sprites. As a piece of scenery is spawned on the horizon, the caching engine checks to see whether that palette is already loaded into the colour registers. If it isn't, it loads it in on the fly. If it is preloaded, then it's reused again. The oldest sprite palettes are always removed from memory first, and we determine their age by the position into the level they are spawned at. A palette with a lower position number is spawned at the start of the level, and a higher position number spawned towards the end of the level. Therefore, a palette attached to a lower position can be removed first. In cases where the palette is already in memory, its position gets rewritten or refreshed to reflect the fact it had been used again more recently. I experimented with a number of different cached slots. Coconut Beach Stage 1 of OutRun is the most palette intensive level. In the end, I settled on 8 slots that could be filled with a 16 colour palette. That's 128 colours total. Too many slots and we would be wasting palette space. Too few and we'd slow the engine down by continuously reloading palettes. The system wasn't bulletproof. I did still need to make some small tweaks to elements of the scenery data to ensure Coconut Beach looked close to the original, but the changes are virtually unnoticeable. This all sounds straightforward, but when it comes to rendering graphics, many Amiga games will simply store the pixel data with a one-to-one mapping to the colour palette. So, a pixel of 0 might be transparent, 1 might be black, 2 will be blue, etc. But in this case, our pixels can be remapped to any of our cached slots based on what other scenery is visible. So, our sprite pixel 2 could be mapped to colour 66, or another time it could be mapped to colour 130, even though the end result is visually identical. In fact, OutRun also uses its palettes in a smart way to reuse the same graphic multiple times by applying different colours. This was done to enable a wider variety of graphics to fit in the 1 megabyte of sprite ROMs. The final colours of the pixel could be different every time, and depending on the palette caching, pixel 2 could be mapped to a number of different entries in the colour palette. This system has some other advantages. It allows us to replicate the horizontal sprite mirroring of the original hardware. Yes, this is what was responsible for inverting the prancing horse on the original game. We can substitute the lookup table for one that not only looks up the corresponding pixel values, but it can also invert the pixel ordering for free. As a future optimization, I'd like to see if I can also cache this step the first time a sprite is rendered, but it would add a lot of complexity to the codebase, which is why I haven't tackled it yet. There are still improvements left I'd like to make, but they're the most complex and dangerous ones. One other cool feature OutRun's graphics hardware offers are the shadows, which are cast across the road surface. The position of these shadows is even adjusted based on the horizontal scroll of the horizon. The arcade hardware generates these colours by passing each underlying RGB value through one of 3 resistors to darken them. The arcade programmer simply sets a special flag on the sprite in question and uses a colour palette entry of 10 to set a translucent pixel. The way in which I achieved the same effect was to pre-calculate the darker shadow colours for every road palette in the game, using a formula to approximate the reduction provided by the resistors. Our first 8 colours in the palette are assigned to the normal colours of the road foreground. The next 8 colours, between entries 8 and 15, are the pre-calculated darkened versions. When a shadow sprite is drawn on the road, rather than manually rereading and adjusting each underlying pixel, I simply OR the existing colour of the road with the value 8. This shifts the palette index 0 to 7 into the range 8 to 15, which are the pre-calculated darker colours. The Python script included with the Amiga version also remaps the pixel data of the shadow sprites in the ROMs so that the value of 0 is transparent and the value of 8 is used whenever we want this shift to occur. The shadow data could then be rendered directly with an OR instruction with no need for a blank pixel test. In fact, it's faster to render shadows than normal sprites as a result of this optimization. One good question that I was asked after I posted the previous video was why I didn't use the copper coprocessor to colour the entire road as well as just the solid background line. And the answer is I would have been writing 16 extra colours per scan line, or writing at least 32 words into relatively sluggish chip memory for AGA. This approach is slower than simply loading those colours into palette registers and leaving them there at the start of a stage. But it's also a good example of how you can identify optimizations in one part of the code base that potentially block other cool functionality elsewhere if you elect to use them. One of the ongoing challenges of a project of this nature is knowing when and where to optimize. Many times I made premature optimizations that I later had to undo. Your code base can grow increasingly complex as you add more functionality and also difficult to maintain, especially as you either optimize or introduce workarounds to make it function on Amiga hardware. So, what other parts of the game are colour hungry? Well, there are a number of static slots that don't get reallocated dynamically in the same way as the scenery ones do. By static, I mean that they are reserved for particular uses and largely remain unchanged for the duration of a level or even the game. The Ferrari reserves one of these, although certain colours of the palette are alternated to create the subtle effect of the tyres rotating. The brake lights are also activated through a palette swap. The original game swaps the entire 16 colour palette to achieve these effects, but as an optimization we only swap the necessary colours on the Amiga. The passengers consist of 2 separate sprites. They aren't baked into the car graphic as you might expect. Originally they each required a 16 colour palette, but this was optimised down to a single shared 16 colour palette for the pair. The smoke sprites and off-road spray are squeezed into an 8 colour entry here. We load the palette for these on demand, as there's never smoke and a spray effect at the same time. The tile map background has 2 layers. Each layer uses a separate 8 colour palette. In the original game, some of these layers used close to 16 colours, so again, these were manually reduced and remapped. During the level transition, we actually need to display 4 separate tile maps simultaneously due to the scroll effect, which is 32 colours, even after the palette reduction. To do so, one of the scenery slots is temporarily repurposed to hold the extra colours. Then it's on to the traffic. There are 6 vehicle types in OutRun that are spawned randomly. There's a lorry, pickup truck, Beetle, BMW, Corvette and Porsche. These vehicles weren't officially licensed, which is why some of them were altered in the recent Nintendo Switch version of the game. Anyway, we've got 6 vehicle types, and actually, once you include all the different palettes they can be, that's over 20 variations. But if we look back at our original palette layout, we only have 3 available slots for the vehicles. Now, as I mentioned on the high score video, the amount of traffic on screen at any one time increases as you progress through the game. 3 traffic slots are enough for earlier levels, but not for the later stages. Sure, I could have reused the palettes, but I didn't want a monotonous effect where the road was filled with identically coloured vehicles. Thankfully, there was a solution. The later stages of OutRun are more simplistic than the early ones. I guess the mentality at Sega was that most casual gamers probably wouldn't get past the 3rd stage or so. As a result, the scenery caching system I explained is adjusted dynamically depending on which level you're on. This allows the level of traffic to be ramped up as you progress through the game, as the traffic slots increase from 3 to 5, whilst the scenery slots are reduced. Finally, some of the remaining colours needed for the fonts and overlays are shoehorned into the remaining palette space. The grey font is squeezed here, but it gets a little crazier. We actually still have some space available, but where? Well, there's 2 interesting details. The first colour of any 16 colour sprite is always transparent. Therefore, we can repurpose that colour entry across all of our reserved sprite chunks to be used for the green variant of the font that we also need. Additionally, the last colour of any sprite is actually a control byte for the sprite hardware. OutRun sprites use an interesting format. They aren't stored as a perfect rectangle. Each horizontal line varies in length and can be an astronomical width of up to 512 pixels wide. This control byte lets the hardware know that the line has ended. Anyway, this byte is also repurposed to the effect that we store additional colours for the top HUD in there. The additional bottom HUD colours are also stored here. Now, different parts of the game somewhat swap this system around. For example, the end sequences work differently once again. But I hope this overview provides an interesting example of why reproducing the rich colour palette of OutRun is still a puzzle to be solved. Even with 256 colours available, we've had to code caching systems, manually rework palettes by hand, reinvent the shadowing system, and of course we still rely on the Amiga's copper coprocessor to change colours every scan line, as discussed in the previous video. One of the disadvantages of going with 256 colours is the impact on overall performance. There's a reason most early Amiga games only used a 32 colour palette. The Amiga graphics display works in bitplanes. Think of each bitplane as a grid full of zeros and ones printed on a sheet of paper. With a single sheet of paper, each entry in the grid can only contain the value 0 or 1, giving us black and white pixels or 2-colour graphics. If we add an extra sheet of paper, we add an extra dimension. This means we can have up to 4 colours because each entry now comprises 2 binary digits. With 3 sheets of paper, we can create values between 0 and 7, and so forth. For a full 256 colours, we need all 8 bitplanes. This starts to require a lot of data throughput because we're effectively writing each value we need to generate our 256 colours on 8 sheets of paper or bitplanes for each pixel. Not only that, but due to the nature of OutRun's real-time pseudo 3D graphics scaling, where hundreds of sprites can be positioned freely, we really need to have per pixel control of our rendering. With the bitplane format, as 8 pixels are packed into each byte on a per bitplane basis, if we need to scroll elements of the screen, we'll need to start performing per byte manipulation. Many Amiga games solve scrolling by using the blitter, but they're generally more traditional 2D affairs and aren't independently scaling and positioning thousands of pixels. The layout of the Amiga bitplane display is ill-suited to 3D style graphics, where a significant number of individual elements have to move independently from one another, And whilst OutRun obviously has 2D sprites, under the hood it's effectively an engine that operates in 3 dimensions. In fairness, Commodore realised their hardware was deviating from where the gaming industry was heading in the early 1990s, and with the success of games such as Wolfenstein 3D and Doom, they introduced the Akiko chip to the CD32 console to provide limited hardware acceleration to the process of converting PC or Mac style chunky graphics to the Bitplane format. Unfortunately, it was too little too late, and to this day many Amigas don't natively have chunky graphics support. In fact, in my port on an 030 processor, up to 40% of the CPU is completely wasted on converting the chunky layout to bitplanes via a software conversion. This really goes to show how fast this port could run if the graphics hardware supported a display format aligned with the VGA PCs of the early 90s. So why on earth did I use a chunky display? Well, the reason for using a chunky format is threefold. 1. Ease of development. I'm scaling freely placeable sprites in real time that run through a caching system to remap the pixels. 2. There's significant overdraw in OutRun. Writing each pixel when factoring in the overdraw up to 8 times is inefficient. 3. Some of the benefits that the Amiga splitter brings are no longer relevant with faster CPUs because they lock you into using slower chip memory. The chunky to planar conversion is also the reason I bordered the game, perhaps the most obvious deviation from the original. By using borders, I can process a smaller conversion window, and the HUD only needs to update on a per component level when something visually changes. And all this is why it's actually a much more sensible idea to develop your own game fully from scratch that plays into the strength of the hardware. It is 100% possible to make a great racing game on just an Amiga 500, but it needs to be designed with the hardware in mind and play into its strengths. OutRun and many other arcade games were designed with their own significantly more powerful hardware in mind, and as such they made for lousy ports to home computers. So that concludes this colourful episode. Maybe not as technically deep as the road hardware episode, but an essential discussion before chapter 3, which is where we're going to dive into real-time sprite scaling and some of the crazy things I implemented to make that happen, and that there'll be some source code to go along with that part as well. So thanks to those of you who joined the Patreon. You motivated me to continue the series. The videos do take a while to make, so thanks for your patience. If you're going to Workbench 25 in Bristol later this month, please don't be shy and say hello. And as you've made it to the end of this video, let me know what you thought and leave a comment below. See you next time.